quite important to know which set you're doing arithmetic in, as the first years who are doing linear algebra 2 and just met the field with two elements at this point will be painfully aware. And yeah, so it becomes important to pin down exactly what a set is. So naive set theory is the idea that we've been working with in our courses up to this point, which is just the idea that any definable collection of objects is a set. Simple enough. And this is fine, kind of 99% of the time or so, but once you start really digging down, as when these mathematicians were asking these questions about the foundations of maths, they were underneath the great maths tree, you find that some of the roots of the maths tree aren't quite as sturdy as you might like them to be. And in particular, this assumption that any definable collection of objects is a set leads to some contradictions. Now, the simplest and best known of these contradictions is Russell's paradox. Who's heard of Russell's paradox? Show of hands. Okay, let's go over it for those of you who don't. So, what we're saying is that any definable collection of objects is a set. So for short, let's say we're saying that anything that says all of the x's such that e of x, where e of x is just shorthand for x has some property. So all of the x's with some property, and we're saying this is a set. We'd like to be able to ask lots of questions about anything we can say is a set. And one of those questions, since sets are kind of about things living inside other things, right? One of the things we want to be able to ask is, for any set x, is x a member of itself? Now, the point is that this gets quite iffy. So, in particular, if we're saying that any set, which we can give a good description to, or any collection of objects we can give a good description to, is a set, then in particular, we can consider the set R, which I'm going to define to be the set of all sets, I'll call it X, I guess, which are not members of themselves. Right. So, we want to be able to ask this question about everything we see as a set. So in particular, we want to be able to ask it about this set itself. So, suppose that R is a member of itself. This isn't real numbers, by the way, this is as defined. If R is a member of itself, then in particular, it has to have whatever the properties that all things that live in this set have, which is that it's not a member of itself. So that's a contradiction. So it must not be a member of itself. But if that's the case, then of course it must fail to have the property that all things that live in R have, which is not, that it's not a member of itself, and therefore it would be a member of itself. So because both answers to this question produce a contradiction, we have a problem. And roughly speaking, what I'd like you to get from this, the way we're going to resolve this problem, is to say that R is kind of badly behaved in some way, right? We want anything that we can give a good mathsy treatment to be well behaved. And clearly, if we can't answer all the questions, or can't ask all the questions that we'd like to be able to ask, it's not a good example. You can think of it as perhaps analogous to a function being continuous. R is discontinuous. It's badly behaved in a way that means we can't do an awful lot of stuff that we'd like to do with it. Oh yes, one other thing before we carry on is that all of the objects that I'm going to be discussing in this talk will be sets. So some versions of set theory contain things which are not sets but live inside sets. And kind of intuitively that's how we work most of the time. But for example, even though we're used to thinking of n as a set, 3 lives inside n, but we're not used to thinking of 3 as a set. So if you do me a favor and just suspend that for a while. Yes, so 3 will be a set for the purposes of this talk, as will 2 and 1 and 0. This keeps things a little bit simpler because it only means that we only have one type of object to deal with, which is nice. Okay, so let's dive right in and meet our first few axioms, because it wouldn't be an introduction to a pure maths topic without some axioms. Okay, so the first axiom, the axiom of extension, just says that 2 sets are equal if they have the same members. Now, this sounds like one of those kind of blindingly obvious pure mathematician things, and that's exactly what this is. If you want to get anything useful out of this, you should think of it as saying that sets don't care what order you write the elements in. So for example, the set containing 1 and 2 is the same as the set containing 2 and 1. And similarly, sets don't care if you repeat an element, and this will be important later on. But for example, the set containing 1 and 1 is just the same as the set containing 1. So we don't care about order or repeating elements, and that's really what this is saying. Next three axioms are a bit simpler. They spring a bit more easily to the imagination. So the first one, the pair set axiom, says that if we have two sets A and B, then we can make another set which contains those two sets. Now, don't mistake this for taking the union of the two sets. It's like if taking the union were taking the box that's A and the box that's B and tipping all the contents out on the floor. This is taking those two boxes and putting them both inside another box. So when you look in the new box, you see two boxes rather than the things that were in them. And the union axiom, the second one, says that if we have a set containing a bunch of sets, then we can take the union of those sets, and that's in exactly the normal way that you're thinking. And the fourth axiom, the power set axiom, is a bit more confusing, but says that if B is a set, then the collection of all of the subsets of B is a set, and we denote it P of B for short. So for an example, we can take 1, 2, and 2, 3, the sets, suppose they're sets. Then if we apply the pair set axiom, we can see that the set containing those two things is a set. And if we apply the union axiom, we can see that the union of the contents of our new set must also be a set. So that's just 1, 2, 3. And again, that's because we don't care about repeating elements. And then, of course, if 1, 2, 3 is a set, then taking the power set of that, we have this horrible mess where sorry, shells, not 5. The empty set is the empty set, as occasionally you call it. Is everyone happy with those three axioms, or would you like me to? In that case, we are ready to derive some immediate conclusions from those three axioms. So, in particular, if we suppose that A and B are sets, then we can apply the pair set axiom to show that the set containing A and B is a set. And then, of course, we can take this new set, if we'd like a letter to use it as called C, we can apply the union axiom to C, since C is a set of sets, and find that the union of those sets, which is just A union B, is a set. And of course, this is the kind of thing that we'd like to happen, because if we were building a set theory, and we started finding that a whole bunch of properties we were used to using didn't work, well, it wouldn't be a very good approach. And in a similar way, because the pair set axiom doesn't demand that the two sets are distinct, just supposing that A is a set, we can take the pair set A, and again, because I said that sets don't care about the multiplicity of elements, that's just the set containing A. And again, to repeat, what we're really saying here is that if these things are well-behaved collections in these important ways, that we can ask all the questions we'd like to ask about them, then this will be a well-behaved collection too, and so will this guy. Okay, let's meet a couple more axioms. So, the axiom of comprehension is a bit like naive set theory, because it's saying, so naive set theory was saying that any definable collection of objects is a set. And all the axiom of comprehension is saying is that you can still say this, provided you restrict yourself to picking elements from something that you already know is a set. And we write sets that look like this quite a lot, right? All of the x's in some other set such that something happens. So that's a good thing to have as well. This is very powerful, and we're going to come back to it a lot. The bloke on the right there, I'm probably going to slaughter his name, is Toralf Skødem, who is a Norwegian mathematician. And he refined this a bit because the original formulation just says something vague about all of the x's such that some property happens. And he made that more precise. So it says anything you can express in terms of logical symbols that we're also used to using is okay to put here, but anything you can't probably isn't. And of course, because we wouldn't be able to prove this one way or the other otherwise, it's helpful to say that the empty set is a set right off the bat. Oh, sorry, the empty set exists. Okay. That makes slightly too much. Okay, but with axioms number 5 and 6, we can prove a couple more things. In particular, if A and B are sets, then we can take the intersection of them now, because we can take, using the axiom of comprehension, we can say that the set of A's in A, such set of A's which are not in B and get A's excluding B, which is also an object that we're used to using. So really what we've given ourselves, in fact, let me rephrase that. So we've kind of derived some immediate conclusions and met the first few axioms. So it's a good point to take a look back over what we've seen so far and see what we can say about them. Now these axioms are a bit weird. If you compare them, for example, to the group axioms, then the group axioms operate in such a way that if you're kind of wandering in the wilds of Southampton and you see a group in its natural habitat, you can pull out your axioms and check, is it associative, does it have an identity, and does every element have an inverse? And just like that, you know whether it's a group. This doesn't happen with sets, right? These axioms don't give us any kind of litmus test to see whether some object is a set. And in a way that kind of makes sense, because the set is such a basic thing that before you've checked whether something is a set, there's not really any way to get a handle on it to perform any kind of test. So instead of what we would do with the group axioms, which kind of operate like this spotter's guide, you can tell whether any object is a group. What instead we're going to have to do is start with axiom 6, knowing that the empty set is a set, and from here, because all the other axioms take the form, broadly speaking, if this thing is a set, then this thing is a set, or if this collection of things are sets, then these things are also sets. And apply those to the empty set, and gradually we'll kind of build up this spider's web of things. So for example, we showed before that if phi is a set, then the set containing phi is a set. And we've also showed that we can take the power set, well, directly from the axioms, we can take the power set of this guy, which is everything, so all of the subsets. So this thing itself, which looks like, yeah, like that. And what else is in there? The only other thing, because, yeah, it's only got one element, so we get the set containing that element and the empty set, because the empty set is a subset of everything. And it's, to begin with, I was imagining that we can go in other directions from here as well and make a kind of big spider's web effect. I can't think of any ways to do that right now, but do you get the picture? That's kind of, so we're going to be building things up rather than identifying them. Okay, so that's all great. So far we've got a whole lot of stuff, but we don't have anything that looks like the kind of objects that we set out to build, right? But we're trying to show that we can build arithmetic out of simpler things. So let's have a crack at building the natural numbers. And to do that, we'll need another couple of axioms. The first one is regularity, which is a bit strange, and it's best to get a handle on the axiom of regularity by using it for a bit. So for now, we'll state it so for any set A, either A is empty, or A has some member such that A intersection that member is empty. Which, for now, just think of it as it's going to be a useful way for us to get a handle on infinity without any messing around with dot dot dots. And lastly, the axiom of infinity says there is a set C, which we're going to treat as the natural numbers. In fact, before I do this, let's define S. That would be a useful thing to do. Okay, so I'm going to use F as a shorthand. It's not really a function, it's something a bit like that. So for any set X, S of X is going to be X union the set containing X, which means everything in here and everything in here. So for example, S of the set containing 1 S of the set containing 1 and 2 will be the set containing 1 and 2 union the set containing 1 and 2. And my curly brackets are probably going to get progressively worse as this goes on, so let's not do that. So everything in here and everything in here, which of course is 1, 2, and the set itself is 1, 2. So in terms of thinking about what's going on here, you're taking everything that was already in X and adding X itself on. And this is going to be analogous to adding 1 to a number, because every time we apply S, the number of, assuming it's finite, the number of elements in S is going to grow by 1. Is everyone happy with that? Cool. A few things to begin with, 3 things back. Okay. saying is going to represent the natural numbers, such that the empty set is in C. For every element in C, S of that element is also in C. And for every element in C which isn't the empty set, then that element is S of some other thing. So really, what this is saying is that if we're thinking of S as plus 1, and we're thinking of C as the natural numbers, phi is going to be analogous to 0, because it has no elements. And I apologize to anyone who's offended by the American natural numbers at this point, but 0 is going to be a natural number for the purposes of this talk. Yeah, so we're saying 0 is a natural number, and for every natural number, that thing plus 1 is also a natural number, and for every natural number other than 0, that's some other natural number plus 1. Does that sound reasonable? Good. Okay, so what we'd like to show is that there's only one set that works like this, because it just makes things easier, right? We can start giving things definite names and treating it like it's only one object. So what can we say about this set right off the bat? So suppose this is C, or a big square.
So sorry, just to point out, because C is a set, it has to satisfy set as well.
Yes.
Because that's really important.
Yes. So yes, because it's a set, it's all of the other axioms have to hold as well. So we've got C. What can we say immediately? We can say the empty set's in C, because we said it was, that's part of the axiom. And because by axiom 2, for everything that's in C, we can apply S, and that will still be in C, we can of course show that S of the empty set is also in the set. And in the same way, we're going to produce an infinite sequence of things going off in that direction, because we'll keep being able to apply S. And what we're really saying is that this is analogous to 0, this is analogous to 1, and then 2, and so on. So what does S of phi look like, just so we've done one of them? Well, we're going to take phi union the second set in phi. So that's everything in here, with nothing in here, because it's the empty set. And what's in here? Just phi itself. So we just get the second set in phi. And this all looks great, but what we don't yet know is that there isn't, so we've kind of got a chain of elements that has a definite start point here. What we don't know yet is that there isn't some other chain of elements. So suppose there's some other element on Y, which I don't know is separate. Because if there were some other element Y, then of course, by the second axiom, we would have to keep taking S of Y, and then S of that, and then so on. We'd get an infinite sequence in that direction. And in the other direction, because Y isn't the empty set, because Y isn't some number of S's applied to the empty set, because of course if it were, it would just be in this sequence and it wouldn't be a separate thing at all, then Y must have come from something, which must have come from something else, and so on and so on and so on. So we're going to use the axiom of regularity to get a handle on this. And what it's really saying is that because when we apply S, we made the set one element bigger. And so of course, when we unapply S, I guess inverse I suppose, we're making the set one element smaller. And for this chain to exist, you have to be able to do that arbitrarily many times. And the axiom of regularity is going to tell us that this is a bad kind of infinity. So what we want to argue is that these elements aren't here. And we're not going to argue that precisely. What we're going to say is that every set satisfying the axiom of infinity is the same. So there's a unique set. And intuitively, that will mean that we've only got this stuff. And this stuff isn't here at all. Although it's very hard to crystallize that intuition concretely. We'll just have to settle for the set satisfying the axiom of infinity is unique for now. Is everyone happy with that before we dive into the proof? Okay. So, suppose we have some A and some B, both of which satisfy the axiom of infinity. The argument I'm going to make in, I suppose, less technical terms, in less technical language, is that if one of these contains some kind of sequence like this, then that sequence, so suppose it's A that has this other stuff in, and B doesn't. I mean, they both could, I suppose, but this is, again, that's something that we can't really get a handle on at this point. So that would mean that A without B had just this stuff in, and none of this stuff. Okay? And if we then consider A without B, pick any element you like from A without B, it's going to look like this. Because of course, if it goes on infinitely, an infinite distance in that direction and infinite distance in that direction, you could have picked one up here, and it would still look the same from there. And that element, this general element from A without B, which of course we've already shown that if A and B are sets, then this guy has to be a set as well. So this general element will have a predecessor. And if we go back to the definition of S, then we know that S of X equals X union X, the set containing X, remember. And in particular, that means, because we're taking union with this bit, that means that always X lives inside S of X. Is everyone happy with that? So, in particular, our general element from this set contains its predecessor. But of course, its predecessor is also in this set. And the axiom of regularity is saying that this set has to be either empty or contain some element such that they don't have an intersection. But we've just argued that because each set contains its predecessor, and A without B also contains its predecessor, then every element has to have some intersection with this guy. So in particular, this must be the empty set, because that's the only other thing that can happen. Let's formalize that then. So, if we apply the axiom of regularity to A without B, on the assumption that A and B both satisfy the axiom of infinity, then we can see that they're either A without B is empty, in which case we're done, or there is some A in A without B such that such that A intersection A does not B is the empty set. But we know that because A is in A, just A on its own this time, and big A satisfies the axiom of infinity, that A equals S of, what should we call it? Let's call it X. For some X in A. And of course, it must also be the case that X is not in B. Because if X were in B, then because B also satisfies the axiom of infinity, we would be able to show that S of X, which we said is A, would be in B as well. And we assumed that A was in A, but not little a was in B, but not B. So we also have that X is not in B. So that means that X is in A but not B. And we also know, because we've always said that we said that X is always in S of X, which is A, that X is in A. So we've managed to find some element in both of these things. Sorry, little a. So the intersection was non-empty. But of course, we started from the assumption that it was. So we have to check this out, and that must happen. So we've shown that all sets which have this structure, which broadly we were trying to argue is a representation of the natural numbers, all have to be identical. And all have to look like that. Is that everyone happy? Okay. So now we move on to something that people may have seen very briefly at the end of number theory in semester 1 of first year. I think we touched on them and then moved very rapidly on. But Peano's axioms for N, which function perfectly well as a set of axioms for the natural numbers in their own right. So if we could come up with a similar kind of set of axioms for the reals, maybe a bit like you met at the start of Calculus 1, and show that we could also build something like that from this more basic set of tools, then what we would have achieved would be something like a unification of the reals and the naturals. We would have kind of brought it together into one thing that hopefully rests on a slightly smaller set of axioms. Point being that we can derive all of these from the axioms that we already have, which kind of pulls it back to an earlier point and makes it simpler. How am I doing for time? Okay. Okay. So we're of course saying that we're defining the symbol 0 at this point to just stand for the empty set, just because we're more used to using it in the context of the naturals as 0. And in the same way, s of 0 we're going to call 1, s of that will be 2, and so on. So the first couple of axioms come almost immediately from the axiom for infinity, because of course, assuming that phi is in n, if we're going to call 0, we're going to call phi 0, and that just means 0 is in n2. And similarly for the second one, that's just a restatement of the second part of the axiom for infinity. The third one is a little bit less immediate, but I hope it's still kind of obvious, right? If k is at least 0, then k plus 1 is at least 1, and in particular it's then not 0. Is that right? The fourth one, yeah, is again a little bit less immediate, but we're also going to skim over, just saying that if k plus 1 is j plus 1, then j equals k, and vice versa. I'd like to zone in on the last one. So this is saying that if we have some x, which is a subset of the naturals, which contains 0, and for all of the naturals, if k is in this set, then k plus 1 is also in this set, then in fact this set is equal to the whole of the naturals. And this is pretty much proof by induction, and we'll formalize that on the next slide. But for now, let's suppose these things. And again, I'll try and put the argument that we're going to make into intuitive terms before we formalize it. So if we start from the assumption that the hypotheses where we can see them. So x is a subset of n such that 0 is in x, and sorry, the empty set is in x, and k in x implies s of k in x. Then, briefly, if we think about the set of natural numbers which are not in x, then this set has to have a least member. And for that least member, because it's the least, that means that one less than it must be in x. Right? So if we consider that one less than our least member that is in x, we'll call that k, then we find that s of k is in x. So we took the least member, and we went back to least minus 1, which has to be in k, in x rather. And then, because we have this as well, we can say that taking s of that, which intuitively is this plus 1 again, which is just this guy, also has to be in x, which contradicts our assumption. So in fact, x has to be equal to the whole of the naturals. Since I'm a bit tight for time, would anyone like to see that in detail, or is that sufficiently glossed over that everyone's happy with it? Okay. So where are we going to go now? Let's do proof by induction. Okay. So the principle of induction says that if a statement is true of 0, true of k plus 1, whenever it's true of k, then it's true for all of the natural numbers. So if we want to prove this, we let x be the set of n in the natural numbers, such that, let's write p of x again as shorthand for, not for x, sorry, p of n as shorthand for this statement is true of n. Now, because the first hypothesis gives us that 0 is in x, and the second hypothesis gives us that k in x implies s of k is also in x, then that's exactly what we had before, right? And from that, we were able to say that x is the whole of the natural numbers. So then if we unwind it from the language of set theory again, that's actually saying that everything in the natural numbers is in x. And in particular, everything in the natural numbers has the defining property that things in x have. So we've kind of boiled proof by induction back to a simpler set of axioms, right? we've managed to give a proof, a proof of proof by induction, or an explanation of it in any case, that doesn't rely on saying dot 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 at any point, which is quite at least it makes it feel more formal, right? But I think this is a simpler set of axioms, even if regularity does seem a bit strange sometimes. Okay. So, yes. One other object that we like to work with quite often is an ordered pair, because of course, as we said at the start, sets don't care about order, right? We would like to come up with some kind of object, A and B, which we'll write with pointy brackets instead, which does care about order, so that two things are unequal if they're the same thing and they're in the same order. Right, this is just like, I guess, coordinates in R2 is the obvious example. We do care about which one's the x and which one's the y. So we could try something like this, but of course that's not going to work because, well, we can reverse the A and B. If A and B were just a set containing A and B, then that would be BA. That's bad. Similarly, we might conclude from that that what we really need to do is introduce some kind of asymmetry, right? Because if whatever our definition of the ordered pair is, of course we want to define it in terms of sets. Sorry, I should have said that. But if whatever the definition is has that kind of symmetry where you can just swap the two of them around, that's not going to work because it's not going to remember the order they were in. So we might want to try something like this. And this looks like a better bet because it has that kind of asymmetry in. But if we cleverly choose our A and our B to reintroduce that asymmetry, so in particular, if we wanted the ordered pair, which is the set containing A and B, then we find that that was this. And that symmetry is back again. So we can swap them around and find that it's this, which not only isn't in the same order, it's actually not the same pair of elements that we started with. So in some sense, this is a kind of weaker equality than just saying that the sets are equal. And that's really bad, because the same order is an additional requirement, so we definitely want it to be a kind of stronger notion. So we can try this guy. And in fact, this is where we end up. There's a simpler version, I believe, where you take the A out of the set, so it's just A and the set containing A and B. But that's a bit more complicated to do stuff with, so we're not going to be discussing that. We can show this is a set as well, and that's just repeated application of the pair set axiom. Because of course we use the pair set axiom to show that the set containing A is a set. And it's clearly easy to use to show that the set containing A and B, that's S, is a set rather. And then of course, sticking those two things into the axiom again will just give us that that is a set. So we know that at least this should be a well-behaved kind of object. And, oh yeah, and just to reiterate, all of these things, even though I'm using little letters for them now, they are also sets in their own right, because it saves us having to deal with any other kind of object. At risk of rushing a bit, let's go on to Cartesian products. So is everyone happy with this? Has everyone met this by this point formally? So R2, yes, is the kind of obvious example because we write that as shorthand for R cross R. It's just the set of all ordered pairs of two things. But the first one is in one set, and the second is in some other set. And we'd like to show that this is a set, to show that the collection, because that, for example, will give us that if R is a set, then we can treat R2 as a set. And we know that that won't do any of the silly stuff that Russel's paradox threw up at the start. So the way we do that is we first take the power set of A union B. So A union B has all of the little a's, which I'm writing as kind of a's, and then with increasing number of primes in A, and b's and the b's with increasing number of primes in B. So if you take the power set of A union B, you get lots of subsets, all of which contain a mixture of elements, some of which are from A, and some of which are from B. And if we take the power set of that again, we're going to get sets of these things. So a set of little sets which consist of elements from A and B. And in particular, some of those are going to look like ordered pairs because we'll have the same, so yes, so they have this structure and also that A is the same as that A. So we've got these, and of course anything that looks like this is in that power set because it has all of the sets that look even vaguely like this. So that gives us a useful thing, because if we know that the thing we want to call A cross B is a subset of this object, then we can define A cross B, because of course I think the top is just that kind of intuitive definition, to be the set of X in the power set of the power set of A union B, such that X is equal to an ordered pair. And this is why the axiom of comprehension kind of, I won't say a get out of jail free card exactly, but it gives us a kind of magic wand in some situations, right? We've managed to build a set that's got all the stuff we want in and some other stuff, and from there we can just say, so we take the stuff from this set that looks like what we want. So, for certain A and A and B and B. Yes, this is the last bit. Let's see if we can get through this. So we would like to define a function as well. And the idea with what we're going to do here is to say that a function is going to be a set of these ordered pairs that we've just discussed. The idea being that, so we've got our function, which is going to be a subset of A cross B, which is of course all of these ordered pairs. And this function, intuitively, is going from A to B. So if we take, yes, of course. So when we write for a particular ordered pair, this ordered pair, when we write that this is an F, this is a really unwieldy way of writing F of A equals B. Everyone begin to see how this might work? So we're going to give ourselves a set of pairs, and if a pair is in this set, then that's saying that the function, which we're thinking of as being the set, takes the first member of that pair to the second member. So how is F going to look? F is going to take some elements from A and some elements from B. So suppose, for example, that A has 4 elements. Let's call them A1, A2, A3, and A4. And B also has 4 elements, B1, B2, B3, B4. So we're kind of envisioning something like this, right? So AB is in F, means that A goes to B when we apply F. What do we not want to happen? Well, we don't want a single element to be taken to more than one place. That would be bad. And in the same way, we don't want to have any elements that don't get taken anywhere. And I suppose by way of analogy, the postman is equally confused by multiple addresses as he is by none. So what do we want to require? We want to require, the first thing, for all A and A, there's a B and B, such that AB is in F. So everything goes somewhere. So this can't happen. It can't be that there are an element that goes nowhere. And for the second point, for all A and A, and for all pairs of elements in the other set, if both of those happen, so if A is matched to B2 and B3, then it must actually be the case that B2 equals B3. And even though it doesn't necessarily look like it, this is something you've all seen before. Because if we cast our minds back again to calculus 1, a function f from B to A, and it'll become clear why I've done it that way around in a second, is surjective if for all A and A there exists a B and B such that A is f of B. And in particular, if we rewrite that, so we've written the bit at the end in terms of f inverse rather than f, you get this. And if we state that in our new set theoretic language, all that's saying is that the pair AB is in f inverse. And if you look back at the top, that means that surjectivity on f is saying the same thing about f inverse we're now saying about a general f in order for that f to be a function. And of course, if you remember, if a function is injective and surjective, then it's bijective. And that's the same as saying it has an inverse. So these two conditions here are like surjectivity and injectivity. We've just written them the other way round, because surjectivity and injectivity of f are conditions for f inverse to exist. So when we don't know that the thing we're trying to check as a function is the inverse of some other function, we're going to have to write them in terms of that function. And this is how they come out looking. And injectivity will do the same thing, it's just a bit longer. So write it out. To the end of everything I wanted to say. Yes. Thank you for listening, everyone. Any questions? Go on.
Who historically came up with the later stuff, like the functions in terms of sets and things like that? Who was that?
I couldn't put a name to that bit, actually. I know.
I just wondered if it was Russel or something you mentioned earlier.
It certainly could have been. That wouldn't surprise me, because that book he wrote about set theory is awfully long. It would be surprising if he didn't get through what I got through in 45 minutes in 300 pages. But no, the honest answer is